Picture this. You're drifting through the vastness of space and a dark, invisible force tugs at your spaceship. It's a black hole, a cosmic monster so dense that not even light can escape its grasp. What happens if you fall in? The journey is stranger and more terrifying than you could imagine. From being stretched into oblivion to experiencing time in ways that defy comprehension, falling into a black hole is a one-way ticket to the universe's most mind-bending phenomenon. Buckle up as we explore the science, the horror, and the mysteries of what happens when you cross the point of no return. But what really happens if you fall into one? Let's follow the journey, step by step, grounded in the latest scientific understanding as of 2025. Approaching the event horizon, the point of no return. Your journey begins as you approach a black hole, say, a stellar mass one with 10 times the sun's mass, located millions of kilometers away. At first, you notice nothing unusual. The black hole is invisible, its presence betrayed only by the distorted light of stars behind it, or an accretion disk of glowing matter spiraling inward. As you get closer, the gravitational pull strengthens. But the real drama starts at the event horizon, the boundary beyond which escape is impossible. For a 10 solar mass black hole, the event horizon, or Schwarzschild radius, is about 30 kilometers wide. As you near this invisible line, the laws of physics remain surprisingly normal for you. You're in freefall, so you don't feel the gravity's intensity. However, an observer watching from a safe distance sees something bizarre. Your spaceship appears to slow down and redden due to gravitational redshift, where light stretches as it fights the black hole's pull. To them, you never quite cross the event horizon, frozen in time as the universe ages around you. This is due to time dilation, a consequence of Einstein's general relativity. Near the event horizon, time for you flows normally, but to the outside universe, it crawls. If you sent a signal every second, an observer would receive them increasingly far apart, seconds turning to years, then millennia. You're not aware of this, but the universe is effectively leaving you behind. Spaghettification, the tidal terror. As you cross the event horizon, things get weirder, and for a smaller black hole, gruesome. The gravity gradient, or tidal force, becomes extreme. Your feet, closer to the black hole, experience stronger gravity than your head, stretching you vertically while compressing you horizontally. This process, dubbed spaghettification, turns you into a thin, elongated strand. For a stellar mass black hole, the tidal forces are so intense that you'd be torn apart before crossing the event horizon. A human body would be stretched into a stream of atoms, long before reaching the core. But what if you're falling into a supermassive black hole like Sagittarius A** at the Milky Way's center with 4.3 million solar masses? Its event horizon spans 24 million kilometers, and the tidal forces are gentler near the boundary. You could cross the event horizon intact, unaware of the crossing because it's a mathematical boundary, not a physical one. For a brief moment, you're still you, floating in darkness with no visible clues of the abyss you've entered. Inside the black hole, beyond the event horizon. Once past the event horizon, you're in uncharted territory. Light can't escape, so you see nothing, not even the accretion disk or stars outside. Your only view might be light that fell in with you, distorted by the warped space-time. General relativity predicts you're heading toward the singularity, a point of infinite density at the black hole's core, where space-time collapses into a region of zero volume. For a 10 solar mass black hole, the singularity is roughly 30 kilometers from the event horizon. For a supermassive one, it could be millions of kilometers away. What happens as you approach the singularity? Physics breaks down. The equations of general relativity suggest space-time becomes infinitely curved, and time itself ceases to have meaning. Your journey ends here, crushed into the singularity's infinite density, or so we think. The laws of physics as we know them fail to describe what happens at this point. You're no longer a distinct entity. Your mass joins the black hole's, adding to its gravitational pull. The role of Hawking radiation, a slow fade. But there's a twist. In 1974, Stephen Hawking proposed that black holes aren't entirely black. Through quantum effects near the event horizon, they emit Hawking radiation, slowly losing mass over time. For a stellar mass black hole, this process takes 10 circumflex, 67 years. far longer than the universe's current age of 13.8 billion years. For you, already inside, this is irrelevant. You're long gone before the black hole evaporates. But to the outside universe, your information, encoded in the particles that made you, might eventually leak out via this radiation, though whether it's recoverable remains a heated debate known as the information paradox. Recent studies, including a 2022 breakthrough by physicists at Caltech, suggest that quantum entanglement could preserve some information in Hawking radiation, potentially resolving the paradox. However, this process is imperceptible to you inside the black hole. Your fate is sealed, but the universe might retain a faint echo of your existence. Could you survive? The firewall hypothesis. Some theories propose a more dramatic fate at the event horizon. The firewall hypothesis, debated since 2012, suggests a barrier of high-energy particles forms just inside the event horizon due to quantum effects. If true, you'd be incinerated instantly upon crossing, rather than spaghettified later. This idea, proposed to resolve the information paradox, remains controversial, as it conflicts with general relativity's prediction of a smooth crossing. As of 2025, no consensus exists, but experiments like those at the Large Hadron Collider continue to probe quantum gravity, hoping to shed light on such mysteries. The cosmic perspective, what it means. Falling into a black hole is a journey of extremes, stretching, compressing, and distorting time and space in ways that defy intuition. For a small black hole, you're torn apart by tidal forces before reaching the event horizon. For a supermassive one, you might survive the crossing, only to meet an unknowable fate at the singularity. Either way, the experience is a stark reminder of the universe's power and mystery. Black holes challenge our understanding of physics, blending general relativity with quantum mechanics in ways we're only beginning to grasp. What's the takeaway? Black holes aren't just cosmic vacuum cleaners. They're laboratories for testing the limits of reality. Observations from the Event Horizon Telescope, which captured images of black holes like M87* in 2019 and Sagittarius A* in 2022, have deepened our understanding, but the interior remains a frontier. Future missions like the planned Black Hole Explorer, BHEX, in the 2030s aim to probe these objects further, potentially revealing more about their inner workings. The final plunge, a thought experiment. Imagine you're an astronaut, equipped with a futuristic suit to withstand tidal forces briefly. You dive toward a supermassive black hole. As you cross the event horizon, you wave to your crew, but they never see it. They watch you freeze and fade. Inside, you're alone in darkness, hurtling toward the singularity. Time warps, space collapses, and your existence merges with the black hole's enigma. Did you experience the universe's ultimate secret, or simply vanish into oblivion? The answer lies beyond our current science. If this cosmic plunge thrilled you, subscribe for more dives into the universe's mysteries. Like, share, and comment to join the exploration, because the next discovery could redefine reality itself.